Seriously, man? We're recording and everything. All right, let's try this again. Algebra 2, Lesson 63. This is understanding the unit circle and radian measures. This is a challenging lesson just simply because most of the time, just the way our brains work, the way most things get taught, is that we work mostly with things in degree form, right? We understand going around a coordinate plane as a system of degrees, whether positive or negative, right? We get the degree kind of system, right? The radian system is not necessarily different, but it's based upon a unit circle, and that can be kind of a hard concept for students to grasp. It can be a hard concept for adults to grasp. But a unit circle is a circle that has a radius of 1 unit, and we're putting that circle on a coordinate plane, okay? Does this make sense so far? We haven't added anything terribly difficult yet, okay? But in my experience, if we start with what you know and what you understand and keep slowly adding one thing after another, that's a good place to start. And then at the moment where you don't understand it, we can take a step back, okay? So you tell me whenever this doesn't make sense, we'll take a step back and then take that step forward again. Does that make sense? Okay, so do we understand a circle? Do we understand a circle laid over the top of a coordinate plane so that the center of that circle is the origin? Okay. All right. Now, a circle has the same radius all the way around, correct? Okay. So we're saying that this circle that exists on this coordinate plane has a radius of 1. Okay? Everything is going to be built around the number 1 in terms of radii. Okay, so far you've measured angles in degrees. We're going to learn how to measure angles in radians. Okay, we're going to be able to convert from radians to degrees and degrees to radians. They're not different, they're just different forms. Okay? All right, so the measure of an angle in radians is based upon arc length. So arc length would be the distance from here to here. Okay? So that's something that's measurable. It's something that can be in inches, meters, yards, miles, that kind of thing. Does that make sense? Okay. So the distance between 2 points on a circle. In a circle with a radius of r, the measure of the central angle theta, which is what's being referenced here, let's say that, and theta is just a Greek letter. Okay, alpha, beta, gamma, you get theta, epsilon, iota, sigma, on down the line. But they like to use theta. Okay, so it looks like this. Okay, so if you see a 0 with a line through it, that's what it is. It's just used as a variable because we get to a point where we may be solving for x or using x as part of a problem, and so we have to use something else to designate the difference between x and something else. So they'll either use x or theta to represent a degree of some sort. All right, so in a circle with a radius of r, the measure of a central angle theta is 1 radian when it intercepts an arc that has a length that's equal to that radius. So if the length from here to here is the same as the distance from here to here, what we're saying is that this angle measure here is 1 radian. Okay? So, and I know we're going to get into it later, but you know, I'm kind of sense that hesitation. I don't understand what radians are. Okay? Somebody give me a relatively common degree. 35 degrees. Okay, so let's say I had 35 degrees and I wanted to convert that into radians. Okay, now radians is going to always be a fraction or ratio in terms of pi. And so how I turn a degree into a radian is I divide by 180. Okay, I divide by 180 and get the fraction. What is 35 divided by 180 as a fraction? 7 over 36. So the radian form of 35 degrees is 7 pi over 36. Okay? So let's try this. Let's say I knew I had 7 pi over 36, and we said we want to turn this back into degrees. All right? One of the things that we're going to learn here in a little bit is that 180 degrees and pi represent the same thing. Okay? So what I can do is if two things equal the same thing, I can substitute. So what is 7 times 180 divided by 36? 35. Okay? So do we see how to take something that's in degrees and turn it into radians? I divide it by 180, and then I put pi in the numerator. Okay? How do we understand how we take something that's in radians and turn it into degrees? Yes or no? Okay, so we've taken a couple of steps forward. Have we taken any steps forward that we didn't understand? Okay, because you feel like I'm walking away from you, and you say, hey, I'm back here, come back, pick me up, I got lost back here. We're all good so far. Great. Okay, so the degree measure of a circle has 360 degrees. We all get that, I think. Since the circumference of a circle is, with a radius of r is 2 pi r, we're familiar with that, the radian measure of a circle is 2 pi radians. Using the conversion 2 pi radians equals 360 degrees, angle measures can be converted between degrees and radians, which I've already showed you how to do. Okay, and I think a little bit of how this is worded is confusing, which is why I showed you this stuff down here. Okay, so we've got this that we can hold on to, right? Okay, because some of this, it comes across more confusing than it needs to be. So like converting degrees to radians, they say multiply the number of degrees by pi radians divided by 180. Basically, we're taking 35 times pi divided by 180, and we're just leaving pi hanging out in that numerator. Okay? So that would convert my stuff into radians. Okay? If I want to convert from radians to degrees, multiply the number of radians by 180 divided by pi radians. That seems really confusing. Okay? Again, I want to, if I'm converting from radians to degrees, multiply the number of radians by 180. Okay? Whatever the radians are, divide or multiply by 180 in the numerator. Okay? Are we all good so far? Okay. Do we need to work out another example? Okay, great. Okay. So let's start with degrees, because if I said somebody give me a radian, probably nobody's going to think of a radian that they could give me. So give me a different number of degrees. 90 degrees. Okay, 90 degrees. Okay. So real quick, how do I convert 90 degrees into radians? Put it over 180. Okay. What's 90 divided by 180? 1/2, right? 1/2. So what is that answer going to be? It's going to have a 2 on the bottom. What's going to stay on the top? Pi. So 90 degrees is the same as pi divided by 2. Okay? And again, we could go back the other way, right? If I wanted to take pi over 2 and turn it back into degrees, what would I do? 180 divided by 2, right? Because I would substitute 180 in for pi. What's 180 divided by 2? 90. I get back to my 90 degrees. Does this make sense? Okay, we can do this. All right, just keep it simple. Well, and for people that didn't hear it on the tape, I just got asked, is this the hardest part as I was flipping to this slide? Okay, so this looks super duper complicated, right? All right, so let me try to simplify it a little bit. What I want you to see is that this is a coordinate plane with 4 quadrants that has a circle laid over the top of it. That circle is what we're calling the unit circle. Okay? Now, the radius of each and every one of these lines is equal to the same length. They're all equal to what? What are they all equal to? That was the whole point of this lesson. No? What's the length of them?
90.
1 unit. They're all 1 unit long. Okay? You with me? Now, there's the other thing I want you to see, and we'll get into this again a little bit later, is that I can begin to find measures by making each of these right triangles. Do we see that I have 3 right triangles here? Okay, and I can solve for different lengths based upon these three different measures of these right triangles. Some of them will be 30, 60, 90, 45, 45, 90. And we see that here, okay? There is a right triangle. Here is another right triangle. Here is another right triangle, okay? Until it begins to look like a spider. Okay, anyway. All right, so for every point, P, X, Y on the unit circle, so those points that they're talking about are these points right here. Okay, so on and so forth, all the way around. And these are certainly not the only points, but these are the most common points. Okay? So for every point P on the unit circle, the value of R is 1 because R is my radius. Okay? Therefore, theta is an angle in standard position. So theta is any of those angles. Okay? So, you know, theta could be this reference angle here, or if I'm looking at this reference angle here. Have I lost anybody yet? Okay, if I need to erase a bunch of stuff and start over, I will. Okay, theta is an angle in standard position whose terminal side passes through the point x, y on the unit circle. So this is what we learned. We learned that sine is what again? Something over something. What is it? SOHCAHTOA, right? SOH. What is O? Okay, sine is opposite over hypotenuse. What is cosine? No. Ka, adjacent over hypotenuse. Tangent is TOA, opposite over adjacent. Okay, opposite over adjacent. So, clear some things back up here. Get our... Gosh. This is right in the middle of this lesson. All right, guys. Okay, so here's what I want you to understand. Sine represents the y-axis because let's say I've got this right here. Okay? Sine is opposite, right? So if this is always going to be my reference angle, it's going to be the angle between my terminal side and the x-axis, correct? So opposite is always going to go there, right? So it's always going to represent an up and down movement, which is my y-axis, correct? Yes? And cosine is always going to represent the x-axis. So better yet than showing it like this, let's show it like this and this. Okay? So cosine, which is adjacent, is always going to represent the x-axis. So that's what you're kind of seeing over here. Y divided by the radius, or y over 1, which is, if I'm just dividing it by 1, it's just y. Same thing with cosine. Now tangent is y over x, or the y-axis over the x-axis, or sine over cosine, which I don't expect you to understand all of that today. Okay, so the coordinates of P can be written as cosine because cosine represents x, comma sine because sine represents y. The diagram shows the equivalent degrees and radian measure. So you see where 180 degrees is equal to -1, 0. Because the x is -1 over here and I'm 0 up and down. Okay? Does this make sense? Okay? Now, 0, 0 or 1, 0 over here can represent either 0 degrees or 360 degrees, depending upon where, if I'm starting or if I'm ending there. Does that make sense? Okay? 90 degrees is 0, 1 because I'm not going left or right, but I am going 1 up. Okay? 270, I'm not going left or right, but I'm going 1 down, so it's 0, 1 in terms of coordinate location. Okay? So you can use reference angles and the portion of the unit circle in quadrant 1 to determine trigonomic function values. And normally I kind of do step 3 first, determine the quadrant of the terminal side of theta in standard position, adjust the sign of the sine, cosine, or tangent based upon the quadrant of the terminal side, determine the measure of the reference angle, and then use all that to find my sine, cosine, and tangent. So I do more of a step 3, step 1, step 2 method. But I kind of need to move around because what time does this assembly start? 2:15, so I don't have a ton of time. All right, one of the things I want you to understand, um, is that in the first quadrant, your sign is always going to be positive. The reason why is because if it's like this, right, and we finish that off, okay, sign is opposite over hypotenuse, right? So here, opposite is positive, and our hypotenuse, no matter what quadrant it's in, is always positive. Yes? Terminal side, okay, so the terminal side is this blue line, okay? So that terminal side can be drawn here, here. Okay, all of these can be terminal sides, okay? Now the initial side is always that red line. Does that make sense? Okay. Okay, so in the first quadrant, and I could go into explaining all of this, why it is, and I did in the other video, and I wish I had recorded it, but the sine is positive, cosine is positive, tangent is positive, everything is positive over here, okay? First quadrant's really nice to work with. But over here, sine is positive, but cosine is negative. The reason cosine is negative is because cosine is adjacent over hypotenuse, okay? So if this is my terminal side, right, that makes this my hypotenuse, but this is my adjacent side over here, which is negative left of the y-axis, correct? And so even though the hypotenuse is positive, because cosine is adjacent over hypotenuse, I'm taking a negative and dividing it by a positive. It's going to end up a negative number. Does that make sense? Okay? And so because sine is going to be here, and my hypotenuse is here, both of those things are positive. So sine stays positive. And tangent's going to be negative because I'm taking opposite, positive, divided by adjacent, which is negative. So I'm going to get a negative. Does this make sense? So you want to look at where those things are in relation and what that ratio is going to do, whether it's going to stay positive or whether it's going to go negative. Am I dividing two negatives by each other? Okay, we get a little bit of that down here. Okay, that's why sine is negative and cosine is negative, because I'm opposite over adjacent, and they're both, one of them is negative, one of them is positive, or sorry, you're dealing with hypotenuse, but your tangent is positive because opposite over adjacent, and both of those are negative. Okay? Okay, if you know the measure of the central angle of a circle and the radius of the circle, you can determine the length of the length s of the arc intercepted by the central angle. And all of this looks really, really super complicated, and it's really not worth describing other than if you know your degrees in radians. If you know your degrees in radians, you can find the length of the arc using arc length equals your radius times your angle in radians. Theta is equal to the degrees of your angle in radians. So if it's not already in radians, you don't want to necessarily use this. We can find arc length without using radians. We do 2 pi r times the measure in degrees over 360. So this is our radian formula for finding arc length. This is our degree formula for finding arc length. Either one can be used. Does this make sense? Okay. All right, I've got that same thing written up here. But what you're solving for when we say arc length is that. It's that red line. Okay? So if we have degrees, we can convert to radians and solve, but we don't need to if we have our degree form. And that's it. We got a couple of minutes here, so with the time that we have remaining, let's do a homework question. Huh? E. Okay. Let's see, we're at 63E. Use a reference angle to find the sine, cosine, and tangent of 200 degrees. Find the exact values. Okay, so I'm going to do a lot of this for you. Okay, isn't that nice? Okay, 210 degrees. 210 degrees. Well, that's going to be in the third quadrant, right? Because it's past 180. So if my terminal side is here, or sorry, my initial side, my terminal side is down here. Okay, so the first thing that I want to do is I want to find out what is my reference angle theta. Okay? Well, I'm at 210, which means I've passed 180 by 30 degrees. All right? So I know that this is 30 degrees here, right? Which means I'm working with a 30, 60, 90 triangle, which means I know that this is 1, I know that this is 2, I know that this is radical 3. Now what I want to do is I know that this is negative because I'm below the x-axis. I know that this is negative because I'm right of the y-axis. Does this make sense so far? Okay? So we want to find the sine, cosine, and tangent of this. So we can say the sine of 210 degrees. Okay, well, let's look at it. What is opposite? -1, right? Over hypotenuse, 2. So sine of 210 is -1/2. Does that make sense? Okay. Cosine of 210. Okay. Well, that is adjacent, negative radical 3 over hypotenuse 2. So that's negative radical 3 over 2. You with me so far? Okay. Let's do tangent. Tangent of 210 degrees. What is opposite of theta? Because it's opposite over adjacent, right? TOA? What's opposite? -1. What is adjacent? Negative radical 3. And remember how we said when we were in the third quadrant that tangent would be positive? Okay, because we're taking a negative divided by negative. Now, can I leave it like this? What do I need to do? Multiply it by radical 3 over radical 3, right? So we know it's going to be positive. What's 1 times radical 3? Radical 3. And what's radical 3 times radical 3? Radical 9. Sure, you could say that. What's the square root of 9? 3. So the tangent of 210 degrees is radical 3 over 3. And that is E in 3 parts. Okay? Does that make sense? I know it's a lot. Hopefully the recording worked this time, and I'll send that out to you when I can.